Quantum foam.
Episode 49, Rocket Science.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
All right, this is episode 49, Rocket Science of Quantum Foam. This is quite an interesting topic. So, what is rocket science? The theory behind blasting something into space isn't as complicated as you might think. Putting it into practice, it is a little bit trickier. Rocket science is all about using rocket propulsion to move anything from a firework to a payload to a manned spaceship. At the heart of rocketry is Sir Isaac Newton's third law of motion. This has been established for over 300 years. Hasn't it, Mr. Newton?
Why, yes, it has.
Right, this is at the heart of that.
Very important stuff.
It says that every action has an equal and opposite reaction. If you stand in front of a wall and push it hard, you will move backwards. Similarly, if you stand on a skateboard and throw a heavy object away from you as hard as you can, you'll roll in the opposite direction. As you push an object forward, the object pushes back on you with the same amount of force. Newton's third law. In a rocket, the object being pushed is the end product of burning fuel, which shoots out the back of the rocket as the fuel burns, forcing the rocket to move in the opposite direction. Rocket science can be complicated, but at its basics, it's not necessarily that complicated. There are three basic requirements to a working rocket: get it moving, overcome the pull of gravity, and plot a course. Each of these depends on physics that has been known since Newton's day.
That reminds me of way back when.
Rocketry in empty space is easy, but on Earth we have to overcome our planet's gravity. This is where a rocket is so much better than a cannon. A cannon has to get its payload up to speed to leave Earth's gravity, the escape velocity, by the time it leaves the barrel, because after that the only forces acting on it are gravity and air resistance, which both slow it down. When it comes to plotting a course, all we need is Newton's physics, which allows us to understand how the flight path will be affected by the gravitational pulls of the Earth, the Sun, and the Moon. The other planets will have influences too, but these are small in a local flight. What makes successful rocketry so difficult isn't so much the science as the engineering. There's so much complex technology in a rocket that it's incredibly tough to be sure that everything is going to work. Imagine building those huge machines that have electronic components, mechanical components, fuel, and many other parts to make a rocket go.
Those self-landing upright rockets are quite marvelous.
In 1920, American rocket pioneer Robert H. Goddard said that a rocket from Earth could reach the moon. The New York Times clearly failed to understand how rockets work. I think they said that it wouldn't work, and it ended up working at some point years later, and they recanted what they had said and updated it to a successful launch. So, how do rockets work? All rockets work by the principle of throwing something out the back to push the rocket forward, but exactly what that something is can vary. One of the earliest known devices using rocket propulsion was the alipile, which was designed by Hero of Alexandria in the 1st century AD. It used steam emerging from tubes to spin a metal ball. That is quite an interesting contraption. Most rockets use flammable substances, and it's the energetic exhaust gases produced by burning them that can provide thrust. Originally, such rockets were powered by gunpowder, but more modern designs use either specialist solid fuel or gases like hydrogen, liquefied to maximize how much can be carried. Space rockets have to be able to work without air, so they need an oxidizer to play the role of of the oxygen in the atmosphere. This might be liquid oxygen or other substances. The newest rocket technology is the ion drive or thruster. This is an electric-powered rocket where charged particles, ions, are accelerated by an electric field to shoot out the back of the rocket. Thrusters are most commonly used for steering rockets as they're very precise but quite weak. However, they could provide the main propulsion for a rocket that was designed for use in deep space. So, how did rocket science begin? Apart from Greek steam rockets, the earliest rockets were produced for firework displays and as weaponry in China, where they date back to at least the 13th century, I think. Metal rockets for weapons began to be used in the West in the 19th century. They were difficult to aim but provided an effective terror weapon and became popular for use from ships as rockets have no recoil, unlike guns. It's this kind of use that Francis Scott Key, the author of the U.S. national anthem, had in mind when he referred to the rocket's red glare. Oh, say, can you see? We all know that tune. It is our anthem. Oh, say, can you see? But when it came to space travel, rockets appeared in stories decades before they were practical. The American establishment first began work on rocketry in the 1930s. The military is said to have found the whole concept too much like science fiction, so the development base in Pasadena, California, was called the Jet Propulsion Laboratory, JPL, even though it never worked on jets, only rockets. I would love to work there. That's a very prestigious establishment. But I'm not a rocket scientist, but I think rockets are freaking cool, and I would really love to go to space one day. I've said it before. I want to go to space. Maybe one day they'll have space hotels in low Earth orbit, and we might be able to go up there for 60 grand or something like that. I want to go to space. Something that's not too unreasonable. Some of these rockets cost a lot of money to send into space. They are sending all kinds of objects out of our atmosphere into space, and it costs a lot of money to do it. Post-World War II, space rockets of both the U.S. and the USSR were initially inspired by the German V-2 weapon. Its developer, Werner von Braun, had little interest in conflict but saw his work as a way to make his space travel dreams a reality. A true pioneer. After the war, both superpowers developed missiles from the V-2, and the Atlas rockets used to get the first American astronauts into space were originally designed as intercontinental ballistic missiles. Even the Saturn V rocket used in the Apollo program had a lineage that went back through the Jupiter series to Redstone missiles. It all came from weaponry. Space rockets carry an oxidizer, such as oxygen or hydrogen peroxide, to enable fuel to burn in space. Yet for the first and hardest part of the launch, they are traveling through the atmosphere. If they could pick up oxygen as they went, it would probably significantly reduce the takeoff weight. So it would be a huge advantage to use atmospheric oxygen while it's available. The problem is that it's a massive technical challenge. In a hydrogen-oxygen rocket, like many used by NASA, the National Aeronautics and Space Administration, the oxygen has to be compressed and cooled to around negative 140 degrees Celsius before it mixes with the hydrogen, which must take place in around 1/100th of a second, while avoiding ice blockages from moisture in the air. Why do big rockets have multiple stages?
It has something to do with the mass.
You often have multiple stages in these rockets. One of the biggest differences between the rockets of early science fiction and the actual ones that took people into space was that the real rockets had multiple stages that fell away as the rocket left Earth. This idea was first developed by Russian school teacher and rocket pioneer Konstantin Tsiolkovsky as early as 1903. The stages reflect the need to carry a lot of fuel to allow the rocket to escape Earth's gravitational pull. When the fuel tanks are empty, they're just extra mass that needs to be accelerated, wasting fuel. Extra mass. By dropping off a stage when its fuel is exhausted or having disposable external tanks like the space shuttle, the remaining craft becomes much lighter, needing less fuel to accelerate it. It just makes sense to dump off the extra weight and the extra mass when sending a rocket into space from the ground on Earth, terra firma. Tsiolkovsky was a theorist, and it was Goddard who constructed the first practical multi-stage experimental rockets. Spacecraft returning to Earth use a combination of air resistance, wings, notably on the space shuttle, and parachutes to slow down the ship on re-entry, unlike most spaceships in science fiction which land slowly under rocket power. SpaceX rockets can re-land themselves on landing pads. That is the technology of the future. The space shuttle looked really cool, though. It was this little tiny shuttle on these big, huge boosters that would get it into orbit. And they used the shuttles to basically build the International Space Station one piece at a time. Rockets are used for landing where there's no air and relatively little gravity, such as on the moon, but a ship simply can't carry enough fuel to make a soft landing on Earth. It uses most of its fuel getting away in the first place. To return to Earth with rockets would need some form of refueling capability in space, which is not currently feasible. There's all the weight that it has to take to get it into space. If we had big, huge fuel tanks chilling in orbit, then we could refuel ships, starships, shuttles, rockets, other vehicles, other spacecraft in orbit. But it's not currently feasible. We just don't have the ability to propel that much fuel into orbit. We use the fuel to get it into orbit and then it's gone. That's basically how it works. Will we always use rockets? Some rockets, like ion drives, are always likely to be useful. But it would be ideal if we could replace rockets, both to get away from Earth and for the kind of long-term acceleration needed to make travel to the outer solar system or even other stars commonplace. One alternative to rockets is a space elevator, but this has its own issues as well. It would basically be a long elevator wire which would power a compartment of some kind that could travel from the surface of the Earth to orbit. It would be like a big long string rotating around the Earth, exactly perpendicular up from the surface of the Earth. We don't have materials currently that are strong enough to build a space elevator from Earth, but this is a possibility and it's been approached in science fiction as a possible solution to getting things from Earth to low Earth orbit. The cable would have to be 38,000 kilometers long. We could probably build a space elevator on the moon, however. That is interesting. I never thought about that.
I remember reading about that.
Oh, you guys read that somewhere? I never read that anywhere. That's pretty interesting. Imagine a space elevator on the moon. Let's get that moon base up and going and see if we can beat China. And let's make sure that everything is kosher with Russia and China as far as setting up shop on the moon. They are going to be doing a flyby this year. By the time you hear this, they will probably have already done it. And in the next year or two, they are going to be doing a touchdown on the moon. Again, the first time in many years. When it comes to deep space, we could replace some of the requirements for rockets with solar cells, which use the pressure of sunlight to gradually accelerate a vessel, or mass drivers, which are like external thrusters that push the whole ship. So, for now, that is what we have for rocket science for this half of the show. I wanted to go into detail about some other facets of rocket science. The physics behind space travel. For as long as humans have gazed up in the night sky, the stars have beckoned with a promise of discovery. The twinkling cosmos ignited our imaginations long before it was ever possible to escape Earth's gravity. Ancient civilizations wrote stories about gods descending from the heavens, and astronomers mapped the stars with wonder. But for now, let's take that midpoint.
Good idea.
Yes.
Hello, I'm Dr. Stephen Hawking.
And I am Sir Isaac Newton.
I am Albert Einstein.
And last but not least, I am Dr. Hezekiah Paul Smith. This is the midpoint of episode 49, Rocket Science of Quantum Foam. Let's get back to the show. Let's get back into it. It wasn't until the 20th century that the dream of leaving Earth became a reality. The vehicle that made it all possible was the rocket. We live in interesting times. They are going back to the moon. We need to be making a moon base on the moon. We want to put more robots out there in space, and we want to put man on Mars. And eventually we want a colony there. I am on board with the three musketeers, myself, Dr. Michio Kaku, and Elon Musk. We are all three constituents on the path laid out by Isaac Asimov in his stories last century. We want to get to Mars. We want our life's work to matter and to contribute to humankind being a multi-planetary civilization. Just in case something happens to Earth, and whatever may happen in the next 1,000 years, we want to set forward a turn of events that will make this possible. Behind the spectacle of launch pads rumbling and trails of fire shooting skyward lies an elegant symphony of physics. Physicists. Rockets are more than metal tubes packed with fuel. Physicists. They are precise instruments born from the marriage of Newton's laws, thermodynamics, fluid mechanics, and the vast realm of astrophysics. Physicists. If you want to learn astrophysics, listen to the Star Talk podcast with Neil deGrasse Tyson. He is probably one of the foremost astrophysicists currently in professional academia. Understanding how rockets work is not just about engineering. It's about mastering the laws that govern the universe itself. Newton's laws, the bedrock of rocket motion. At the heart of rocket propulsion are Isaac Newton's laws of motion. The third law. When a rocket fires its engines, it expels mass in the form of high-speed gas out of its rear nozzle. The action is the ejection of gas. The reaction is the forward thrust of the rocket. Unlike a car that pushes against the road or a plane that relies on air, a rocket doesn't need anything to push against. It creates its own push by hurling mass backward using chemical energy. Newton's first law explains why rockets need to overcome inertia. At launch, the rocket is at rest, and only a net force, thrust exceeding gravity, can change its state. Newton's second law, force equals mass times acceleration, or F equals ma, gives engineers the precise relationship between the force required, the mass of the rocket, and the acceleration needed to escape Earth's pull. What is thrust? Thrust is the force that moves a rocket forward generated by the expulsion of exhaust gases. The amount of thrust a rocket can produce depends on two main factors: the mass of the exhaust leaving the rocket per second and the velocity at which it leaves. This relationship is captured in a fundamental equation known as the thrust equation. Thrust equals mass flow rate times exhaust velocity. This is a direct application of Newton's second and third laws. The higher the exhaust velocity, or the more mass ejected per second, the greater the thrust. To maximize efficiency, engineers design engines to release gases at incredibly high speeds. In chemical rockets, this means harnessing violent reactions that convert solid fuel or liquid fuel into superheated plasma, exiting the nozzle at thousands of meters per second.
Wow, that's fast.
One of the most unforgiving aspects of rocketry is known as the Tsiolkovsky rocket equation, named after the Russian scientist Konstantin Tsiolkovsky. We mentioned this. He derived it in 1903. It expresses the change in velocity a rocket can achieve based on its initial and final mass and the exhaust velocity of its propellant. This equation defines what is often called the tyranny of the rocket equation. To reach orbit, you need a specific change in velocity. For Earth, around 9.3 to 10 kilometers per second is the escape velocity. Achieving that with chemical propulsion requires staging, where parts of the rocket are jettisoned to shed mass and improve efficiency, as we described earlier. Staging. Shedding weight for the win. Multi-stage rockets are the solution to the mass problem. Instead of building a single giant rocket to go all the way to orbit or beyond, engineers divide it into segments or stages. Each stage has its own engines and fuel supply. After a stage runs out of fuel, it is detached and left behind, and it detaches, making the remaining rocket lighter and easier to accelerate. The famous Saturn V rocket that took astronauts to the moon had 3 stages. The first stage burned in just 2 minutes, providing the brute force to lift off the pad. The second stage carried the rocket higher, and a third stage put the spacecraft into orbit and later pushed it toward the moon. Without staging, chemical rockets simply couldn't carry enough fuel to escape Earth's gravity well and still have room left for cargo or humans. Fuel and propellant, the fire in the belly. Rocket fuel isn't like gasoline. It's a highly specialized substance designed to deliver enormous energy in a short time. There are 2 broad types, solid and liquid propellants. Solid propellants are mixed into a solid form that burns from the inside out. They're reliable, simple, and can be stored for long periods, making them ideal for missiles and boosters like those on the space shuttle. Once ignited, however, they can't be turned off. Liquid propellants are more flexible. They involve separate storage of fuel like liquid hydrogen and oxidizer like liquid oxygen, which are pumped into a combustion chamber where they ignite. Liquid engines can be throttled, shut down, and restarted. Crucial features for precision maneuvers in space. They need to be able to turn the rocket on and off. This is possible with these liquid propellants. In both cases, the propellant must do 2 things: provide mass to throw out the back and energy to do it quickly. The energy comes from chemical reactions, while the mass becomes the exhaust. Some advanced concepts use electric or nuclear energy to heat or accelerate propellant. These systems are more efficient, they have a higher exhaust velocity, but provide much less thrust, making them suitable for deep space missions rather than launch. Escaping gravity from launch pad to orbit. When a rocket launches, it must overcome Earth's gravitational pull, known as escape velocity. However, strictly speaking, rockets don't launch straight up just to escape gravity. They launch upward to get out of the dense atmosphere, then curve sideways to achieve orbital speed. To stay in orbit around Earth, a spacecraft must travel sideways at around 7.8 kilometers per second. It's not so much hovering as falling around the Earth, constantly falling towards the planet but moving fast enough that the ground curves away beneath it. This orbital dance is governed by gravitational and centripetal forces, and getting into this delicate balance is what consumes most of a rocket's fuel. The launch trajectory is a carefully calculated arc designed to maximize efficiency and minimize atmospheric drag. Once in orbit, rockets may fire again to adjust position, transfer to higher orbits, or leave Earth's gravity altogether on interplanetary journeys. The role of vacuum and atmosphere. On Earth, airplanes need air for lift and for engines to burn fuel. Rockets, however, carry their own oxidizer and work in the vacuum of space. In fact, rockets become more efficient the higher they go because there's less atmospheric drag and no lost pushing against air molecules. In the lower atmosphere, however, rockets face enormous resistance. That's why most launch trajectories are designed to minimize time spent in thick air. Rockets also throttle back during the period of maximum aerodynamic pressure known as max Q to reduce stress on the vehicle. Nozzles are designed differently for vacuum versus atmospheric use. Sea-level nozzles are shorter and optimized to expand gas efficiently against surrounding air, while vacuum nozzles are much wider to allow gases to expand fully in the low-pressure environment of space. Heat, pressure, and engineering marvels. Rocket engines operate at extremes. Combustion chambers can reach temperatures above 3,000 degrees Celsius. Pressures inside can exceed 100 times that of the atmosphere. Yet the walls of these engines must remain intact and often cool enough to avoid melting. To manage this, engineers use regenerative cooling, where the cold propellant is routed through channels around the engine to absorb heat before entering the combustion chamber. This not only prevents engine failure, but also preheats the fuel, improving efficiency. Materials science is key when dealing with the construction of these rockets. Rocket parts are made from exotic alloys that withstand temperature changes, vibration, and mechanical stress.
I was going to mention, it was a coincidence that you just happened to record this episode on rocket science on the exact day of the 40th anniversary of the Challenger space shuttle accident.
That is crazy.
Tolerances are razor thin. A microscopic crack could spell catastrophe.
Or the O-rings freezing.
Guidance and control. The rocket's brain. Rockets must be steered with incredible accuracy. This is achieved using guidance, navigation, and control systems that adjust thrust and direction mid-flight. Small engines called vernier thrusters or reaction control systems can tweak orientation. Gimbaled engines, those that pivot, can direct thrust for steering. Gyroscopes and accelerometers detect changes in position, feeding data to onboard computers that make real-time corrections. In modern rockets, computers handle most of the guidance, but ground control monitors every phase. A slight miscalculation in angle or timing can result in a failed mission or a lost spacecraft. Human spaceflight. Rockets that carry life. Sending humans into space adds layers of complexity. It's very hard to do this, and we want to make sure that these machines that we build, the rockets, are able to support life. Life support, escape systems, shielding, and safety redundancies must be integrated into the rockets. Rockets like NASA's Saturn V or SpaceX's Falcon 9 with Crew Dragon capsule are engineered with these considerations. The forces on launch can be brutal, up to 3 Gs of acceleration. Vibration, heat, and noise test the limits of human endurance. Every system must be fail-safe. The margin for error is nearly zero. Re-entry is equally harrowing. A spacecraft returning to Earth must slow down from orbital speeds and survive the fiery descent through the atmosphere.
There was also the Columbia Space Shuttle that burned up in 2003.
Heat shields absorb and deflect temperatures that would melt metal. Traditionally, rockets were for single use and are discarded after a single flight. This makes space travel extremely expensive, but this is definitely changing. SpaceX has pioneered reusable rockets with the Falcon 9, where the first stage lands back on Earth for refurbishment and reuse. They use them at least 10 times or more, but they reuse them fairly often as long as they don't blow up. They've went through a period where they tested multiple rockets and they have been able to land them back upright on barges and landing pads out at sea. This innovation is transforming economics, enabling more frequent launches and reducing waste. Blue Origin and other companies are following suit, heralding a new era of space access. The future may also include massive launch systems like SpaceX's Starship with 33 engines, designed to carry cargo and humans to Mars. Nuclear engines, space elevators, and even antimatter propulsion are being studied, promising even greater reach. I am more interested in antimatter propulsion as well as antimatter communication, being a computational physicist.
That's how the spaceships are propelled in Star Trek.
That is essentially rocket science for you in a nutshell. But for now, this concludes episode 49, Rocket Science of Quantum Foam. See you guys later.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.